This is the video submission of Team 1128. Our team members consist of Manuel, Lisondra, Angelo, Sodejana, and Dominic, Manginsay. Our team coach is Dr. Leonard, Paleta, and we're from the University of Southern Mindanao in the Philippines. And for the SCUDEM challenge, we chose to analyze and develop a model for problem A, sweet tooth and heavy metal. Our recent study demonstrated that some chocolate products may have high levels of heavy metal. Eating contaminated chocolate may lead to bioaccumulation of heavy metals in the people who eat the chocolate treats. Our task is to track the long-term accumulation of heavy metals in the people who eat contaminated chocolate. Our general objective is to construct a model that will track the long-term dynamics associated with heavy metal levels for an individual who consumes contaminated chocolates. Specifically, we aim to answer the following questions. First, will the trend associated with heavy metal levels be different for a child whose birthday is a long time before and after other major recurring holidays? Second, is there a difference in the heavy metal if a parent has children consume their treats over a long period after a holiday rather than allowing a child to binge during the holiday?
For our assumptions, we assume that the accumulation of heavy metal in the body was solely due to consumption of contaminated chocolates. In all scenarios, chocolates consumed are contaminated. Heavy metals in this analysis were limited to lead, cadmium, and arsenic only. Heavy metals present in the chocolate are fully absorbed by the body once consumed. Bioaccumulation of heavy metal was measured based on the level of concentration of such heavy metals in the body. Long-term analysis will span at the end of 3 years, starting from January 1. We assume that at T equals 0, the amount of heavy metal in the body from chocolate consumption is 0. Daily consumption of heavy metal from contaminated chocolate for non-holiday is the same as an average heavy metal in contaminated chocolate, measured in micrograms per day. Binge consumption during holiday and birthday is defined to be 4 times the average consumption. The rate of elimination of the heavy metals were derived from its half-life within the human body. Holidays and birthday use in the analysis were pre-specified and ensure possible scenarios helpful in the analysis were taken into account.
For our model, we modified the decay rate equation to incorporate the average heavy metal accumulation of the body from the contaminated chocolate consumption, taking into account the days where there is a binge consumption. In this model, we have the normal decay rate given by the elimination constant K multiplied by the amount of heavy metal accumulated as a function of time. Here, K is calculated from the half-life of the metals within the body. The variable C is the average daily accumulation of heavy metals from the contaminated chocolate, while the discrete consumption during birthdays and holidays are given by the Dirac delta function. This ensures a spike in the heavy metal accumulation at certain days of binge eating, while quantifying for the random consumption as average uniform consumption of chocolates. We solved our model by taking the Laplace of our differential equation, which gave us the equation 1, where the initial heavy metal in the body is denoted as m sub 0. Taking the inverse Laplace of equation 2, we get equation 3 denoting the amount of heavy metal accumulated as a function of time. Just like the regular decay rate equation, the presence of a negative power in the exponentials ensures that m converges to a certain value. We also see that our solution yields a unit step function given by this definition below, which ensures that the heavy metal accumulated from the binge days can only be taken into account once a holiday or a birthday appears, like a switch, which then continuously decreases once it is turned on due to the presence of a negative power on the exponential. The remaining variables are shown in this slide.
Our strategy in order to answer the questions at hand is to track the long-term dynamics of each heavy metal separately for lead, arsenic, and cadmium. Therefore, we will need some numerical constants that will be helpful in our analysis. For the elimination rate denoted by K, as said earlier, we derived it from the half-life of the different heavy metal in the human body. The average daily accumulation of heavy metal from contaminated chocolates denoted by C was obtained from the attached research in the bibliography of problem A. During special occasions like holidays and birthdays, we presume that consumption is higher than the average daily accumulation. Hence, for R sub B and R sub H, we assume that the values are 4 times the average daily accumulation C. We specify 6 major holidays that usually involves large consumption of chocolates. For birthdays, we specify 3 scenarios which are near holidays in the earlier and later part of the year, January 23 and November 12 respectively, and not near any major holidays. The case for this analysis is set to be September 1.
To simulate our model, we use the for loop command in Python to simulate the switch that incorporates the contribution of the heavy metal accumulated at binge days, which is described by the unit step function from the model. Shown here is the plot of the lead accumulation for a span of 3 years, as well as the total lead accumulated each year, given that the birthday of the consumer is between major recurring holidays earlier in the year, which we set as January 23 in between January 1 and February 15. The binge consumption during holidays are marked by the red dotted lines, the birthday is marked in green dashed lines, and the end of the year is marked by the yellow solid line. These binge consumptions are modeled by the unit step function. We also show here the plot of the lead accumulation for a span of 3 years but for a birthday in between major recurring holidays later in the year, which we set as November 12 between Halloween and Christmas. Lastly, we also have a plot of lead accumulation during a birthday that is far in between major recurring holidays. We also have plots of arsenic at the same birthdays, but a more consistent trend with constant year-end values due to its large value of elimination rate constant. Lastly, we have the plots of cadmium which yield large year-end accumulation values due to its very small elimination rate. Here given are the tabulated values for the total heavy metal accumulation at the end of the year in the span of 3 years for different birthdays. We see that cadmium has the largest contribution due to its extremely low elimination rate constant, while arsenic has the least contribution due to its larger elimination rate constant. We also saw that the total accumulated heavy metals give the largest values during the major recurring holidays later in the year, which is November 12 in between Christmas and Halloween, while least during earlier in the year between January 1 and February 15. An obvious trend that we see from the tabulated values is the existence of an asymptote, which is approximately equal to the average daily consumed heavy metal over the rate constant K. For cadmium, this asymptote is too large that it takes more than 3 years to go even close. Now, one interesting case in this model is to see how it behaves when instead of a binge consumption at certain holidays, we distribute the amount of accumulated metals in a span of a year, which implies gradual consumption after holidays. This can be done by first multiplying the binge consumption values by the number of holidays plus the birthday divided by 365 days and added to the average daily heavy metal consumption while we set the holidays and birthdays to 0. Choosing one birthday, we compare the plots between these two cases and see that we get a smooth behavior for the gradual consumption case. We also see this trend from the arsenic and cadmium accumulation. From these tabulated values comparing the two cases, one where there is a binge eating that occurred and the other is simply gradual consumption, we see that in both lead and cadmium, there is a higher total accumulated metal after 3 years when there is a binge consumption compared to the gradual consumption, while an opposite trend is seen in arsenic. This may be attributed to the ratio of the average consumption of the heavy metals over their decay rate constants. In total, however, we see that gradual consumption yields lower heavy metal accumulation by the end of 3 years.
Conclusion. In the long run, consumption of contaminated chocolate results to higher levels of accumulated heavy metal in the body. These levels are high enough that they are considered toxic and could cause heavy metal poisoning. Based on the analysis, higher amounts does not depend on whether or not the birthday is long before and after major recurring holidays, but rather whether or not the birthday is near the end of the year. Lastly, gradual consumption of contaminated chocolate after a holiday leads to a lower total accumulated heavy metals compared to binge behavior at holidays.
Here are the limitations of our study. The estimated accumulation of heavy metal obtained at certain time t assumes each day the individual consumes chocolate. In other words, our analysis did not take into account the days where an individual skips eating contaminated chocolate. The elimination rate K in each heavy metal was approximated based on its half-life in the human body. not its rate of elimination through excretory organs.
In addition, the model also assumes no interaction between the heavy metals, and lastly, it does not take into account other sources of heavy metal accumulation such as contamination in soil and drinking water, among others. Thank you for listening.